Okay, welcome everybody to the INQA seminar for today, 7th of May. It gives me great pleasure today to introduce our speaker, who is Anthony Ciavarella, who is currently at Lawrence Berkeley lab, but I think is going to be talking about stuff he primarily did at the University of Washington while he was a graduate student there. And he'll be talking about adiabatic preparation of the Heisenberg model ground state. Anthony, over to you.
All right, thank you. Yeah, so before I get started, I just want to mention my collaborators on this work. So, like you said, this was done when I was at the University of Washington, working as a resident with Martin Savage. And so the work was done in collaboration with Stefan, Hirsch, Henry, and Nikita, and then also Pavel Lugovsky at AWS. And so the work I'll be talking about today mostly is in this one paper, but there are some related results across all four of these. So before I get going, I also want to mention that by training, I work in nuclear theory. I'm interested in studying the properties of QCD. And so the way we explore the non-perturbative aspects of QCD is through numerical simulation. And so my interest in quantum simulation sort of grows from there. And so the way we typically study QCD numerically is through a lattice formulation where we take space, we break it up into a discrete lattice, and we place our fields at points on the lattice or on the links between sites. And so on traditional classical computers can study this, the theory with Monte Carlo simulation that allows you to extract things like hadron masses, static properties like form factors, field computed contributions to mu on G minus 2. But this program has limitations due to the presence of sign problems. So for example, you can't use Monte Carlo to study real-time dynamics or inelastic scattering or thermalization. And you also have issues with finite density systems as well. And this is less than ideal from our perspective because these are things that exist in the real world that we would like to be able to make predictions from theory. And so fortunately, quantum computers, we expect to be able to probe real-time dynamics directly. And so we expect if we can map our theory onto a quantum computer, we can use it to compute these quantities without having to deal with the presence of a sign problem. And so, yeah, the long-term goal is to perform a quantum simulation of QCD. That QCD is kind of a complicated theory with both fermions and gauge fields. And so along the way, we can use simpler toy models to help us develop simulation techniques. In particular, the toy model we use in this work is the O3 nonlinear sigma model in 1+1D. It's the simplest quantum field theory that you can write down that is asymptotically free like QCD. So we expect simulation techniques that work for this will help teach us about how we can simulate QCD on quantum computers a bit better. So this is just the action that defines the 3 model. So it's just given by the partial mu phi dot partial mu phi, where phi is 3 vector with norm 1. And so you also see this field theory coming up to describe antiferromagnetic materials. But for us, we're interested in it as a simpler toy model of QCD. And so you can use the antiferromagnetic Heisenberg model as a lattice regularization. So what I mean by that is if I take this Hamiltonian defined by summing over sites in the lattice with this S dot S type interaction with certain lattice geometry, you can recover this quantum field theory. And so it's shown in this work that if you use this comb type geometry where you have a line of qubits with then single ones sticking out, you reproduce this O3 model. And another approach that people will explore as well is using a rectangular lattice where one direction is taken to be small, the other is significantly longer. And you can also show in this case as well that you recover the O3 model. And so we'll use these formulations as our Hamiltonian for our lattice regularization of the O3 model. And so as a first step towards doing a non-trivial simulation that we'd be interested in, we need to prepare the ground state. Since we're interested in scattering, that's going to be done by creating excitations on top of the ground state and interacting them. But before you can do that, you actually have the ground state prepared on your quantum simulator. So when it comes to quantum simulation, there's a couple of different approaches that you can use. One is digital, where you have a quantum computer with a universal gate set, and you construct all of your operators out of these universal gates. This requires a fairly high degree of control over your experimental setup. So another alternative you can use is an analog simulation, where you have some experimental setup and you engineer it so that it reproduces the Hamiltonian that you want to simulate. And so generically, you can usually do this with a lot less level of control of your system, which makes it something more suitable for near-term implementation. And so in this work, we assumed that we'd have access to experimental setups described by the Ising model with this ZZ term and then this single qubit term. And so the reason we picked this is because there's multiple experimental platforms, such as superconducting qubits or neutral atoms, that can reproduce this Hamiltonian. And so now we've fixed the Hamiltonian for our experimental platform, we need to figure out how to engineer the Heisenberg S.S type interaction on there. And so we found a way to do that at periodic times. Okay, I should stop and say that if at any point something I'm saying is not clear, feel to interrupt me and ask questions. But yeah, so at periodic times, we figured out a way to reproduce the evolution of the Heisenberg model. So you take your drive field to be omega to be large, and you set the parameters omega x equals omega sine theta, omega y equals 0, and omega z equals omega cosine theta. And you switch to interaction picture where you take these to generate the free part of your evolution. You can show that at times 2 pi over omega, you'll reproduce the evolution of the Heisenberg model up to 1 over omega squared corrections. And so you can engineer the Heisenberg model up to corrections that go as 1 over whatever field strength you can engineer. And so yeah, by changing theta, you can also vary from the fully symmetric Heisenberg model to more of an XXZ type model. But for this work, we're really interested in the symmetric case where all of these terms have the same coupling. And so now we like to use this to somehow prepare the ground state. So we know that if these two Hamiltonians reproduce the same time evolution operator at these discrete times, then they would have to have the same eigenstates and have energy levels that agree up to integer multiples of our field strength omega. And this isn't exactly true. We know it's true up to 1 over omega squared corrections, but it's good enough to know that they should have.
I'm sorry, I might have missed it, but what is the relationship between the parameters of your physical Hamiltonian and the J in your Heisenberg model that you're simulating?
So the J in the Ising model, which we assume are just going to be fixed by whatever experimental platform you're using, are the same as the J in the Heisenberg model. So it's a one-to-one correspondence.
I see, thanks.
Yeah, so we know that they should have the same eigenstates up to 1 over omega squared corrections. And so this gave us the idea that we take this Ising Hamiltonian and with some large omega, and we adiabatically varied theta from 0 to the angle we need to reproduce the Heisenberg model evolution. That should take us from product ground state into the Heisenberg model ground state. And so we call this technique the adiabatic spiral, because if you look at how the Z term would, like a single poly Z would evolve in the interaction picture, looks like the sort of spiral shape on the Bloch sphere. And so to get to the ground state, you would need to start from this antiferromagnetic Neal state. And so generically, this in your initial state, your energy levels will be degenerate, but you can split them through the addition of this position-dependent Z term. So I should also mention that you don't actually really need to prepare this alternating state on hardware, because you can just do a basis change on every other qubit and begin with the all spin down state, and then you just have to introduce some alternating sign in your dry field. And so now to check that this works, we did some numerical examples for small systems. So first thing we looked at was the comb that I mentioned before, where it's described by this Heisenberg model Hamiltonian, where we have one coupling for the qubits along this line, and then a separate coupling for the qubits that are jutting out like this. And so now to implement the adiabatic spiral, you need a Hamiltonian that evolves under this, where we have separate J's for two directions, and we have our Z term, the X term we turn on adiabatically, and then this penalty term that we would use to split the degeneracy. And so just for the system, we did a very simple example, taking the two J's to equal to 1, and then a linear turn on. And then here we just set the penalty term equal to 0, so we expect to end up in an equal superposition of the ground state and the first excited state. And so we looked at this for fixed time as a function of omega. So this black dashed line shows the energy of the ground state, and this red dashed line shows the energy of the first excited state. And you can see that at small omega, you end up nowhere near either of them. But as you take omega larger, you see that the adiabatic is actually taking you to a mix of the ground state and the first excited state in the Heisenberg model, while evolving the system under this Ising Hamiltonian. So this is all fine, but we would like to actually look at implementing this on quantum hardware. So as first toy example, we looked at trying to implement this on D-Wave's quantum annealer, which is described by this Hamiltonian, where you have this A function describing your sum over X qubits, and then this B term that describes multiplying your Z's. And so A and B are fixed by D-Wave, and the only thing you can program on their system are your H's, J's, and this path S of T. And so you can try to use the reverse annealing function to do this. And so it shows the values of A and B that you would use to do this. So you can begin with A equals 0, and then take B at its starting point, then slowly ramp up down to where the point you would want, where the evolution would be described by the Heisenberg model. However, to perform a measurement on their hardware, you need to finish the simulation at a point where A is set to 0. So we tried to punch that term off. And so using the parameterization of A and B that D-Wave provides, we did some simulations on classical computers to see what sort of energies we'd expect to come out. And so here on this plot are different values of J we tried. So this black dashed line is the energy of the ground state. The red is the first excited state. And this gray dashed line is the energy of the initial state. And we tried various energy penalties as well. And so you can see that for a very large number of them, or the result is that you end up back at the initial state. And so if you look at this as a function of the switching time, what happens is that during the adiabatic process, you actually really are, the spiral is working and taking you to a low energy state. But during the process of turning off the dry field, the quench is not quite fast enough to actually be a quench because the size of these terms, that evolution is still effectively adiabatic. And so you just adiabatically go back to your initial state.
Anthony, sorry, is this a two-qubit system or a multi-qubit system or what?
This would be same example as on the previous slide, so 8 qubits.
Great. Okay.
And this was not run on their hardware. This is just classical simulation. So like no effects of noise are in here. Yeah, so I should mention that this is very much not how D-Wave's hardware is designed to be used. So it's not too surprising that we weren't quite able to make it work on here because their hardware is designed to do adiabatics. It's not designed to do this quench at the very end. So the issues we found in superconducting, we looked instead at a neutral atom implementation. And so neutral atoms, we know, can also be described by the Ising-Hamiltonian as given here, where you have this global X term, and then you have this, well, n hat term that is really just 1 minus d over 2 with some detuning strength, and then this van der Waals interaction that depends on where you place the atoms. So we can consider implementing the adiabatic spiral with constraints based on previous experiments that have been on neutral atom platforms. So we pulled numbers from this paper from Lucan's group from 2021, where they had a max dry field strength of 2 pi times 4.3 megahertz, a coherence time of 3 microseconds, and use a lattice space. Well, in our simulations, use a lattice spacing of 10.5 micrometers. So we considered 2 different approaches, one using our adiabatic spiral, another using a sort of trotterized time evolution approach, where you would try to implement a ZZ evolution, then an XX, then a YY, and then just loop through those in a periodic manner. And so here is showing the energies that we got out. And so the units on this are in units of J from the Heisenberg model, not in units of microseconds. This blue line shows the point where 3 microseconds would be. And so that's where you assume that we couldn't run any longer. And so you can see that within this constraint, the adiabatic spiral is able to get you down to a state with energies between the ground state and the first excited state. And if we had longer evolutions time, in principle, it could get us even closer to the vacuum state. And so this example was done for the comb as from the previous page as well. But for purposes of simulating the O3 model on neutral atoms, it's not the most efficient layout we can consider using because in these setups, they can really lay down a full 2-dimensional array of atoms. And so if we're laying down the cone, we're really doing sort of a 1D line, and we're not really making full use of the simulator. So this is where we'll switch to the other last regularization I mentioned, where you have an antiferromagnetic Heisenberg model on a rectangular lattice with the y direction taken to be small and the x direction taken to be large. And so given that it seemed that the adiabatic spiral can get us close to the ground state for the cone layout, we wanted to have some observables we could use first to check that our lattice regularization was really reproducing the physics of the quantum field theory we want to study. So we did that through computing a renormalized coupling G, which is defined in terms of the lattice size and then eigenvalues of a 2-point function here. And then we computed the step scaling function where we compute G on 2 different lattice sizes and take their ratio. And so this is a sort of the lattice equivalent of computing a beta function. And so we use sensor network simulations to extract the 2-point function for the ground state of the Heisenberg model. And so with the one we'd be able to engineer on neutral atom hardware would be this S.S type interaction with this van der Waals potential with an alternating sign. So nearest neighbors would be antiferromagnetic, and then next to nearest neighbors would be ferromagnetic, and then that would be antiferromagnetic. And so we used DMRG to compute this step scaling function. So this plot we have the blue dashed line, which is a perturbative result calculated directly from the O3 model and continuum. And then this black line is also classical calculation of the continuum quantum field theory as well. And then all the points are just different ratios of X and Y lattice spacings to test that this Hamiltonian is actually reproducing the physics of the O3 model. And so we can see that for the last that we tested out, that you're actually reproducing the step scaling function correctly, which is a pretty strong sign that you are really able to reproduce the continuum physics of the O3 model. So for the last sizes using this, we had Ly equals to 6, and then the smallest Lx we used was 6 as well. So this really tells you, like, once you have a setup of like 36 atoms or so, that is sufficient to start thinking about the continuum limit of quantum field theory, which to us was very surprising because kind of assumed that you would need a much larger quantum simulator to do this. But it turns out 36 qubits is good enough to start. And so now we'd like to know whether or not we can actually prepare the ground state on neutral atom setup. And so before we looked at just implementing the adiabatic spiral. And so, but to check whether or not you can work at these system sizes, you can't really do exact simulations. So we use tensor network simulations again to check how this works for system sizes like 6x6, where we and 8x6 lattices. So in this table, we have the spacings between the atoms that we put in the simulation, and then the final energy that came out in terms of the energy gap. So you can see that through the adiabatic spiral simulated with the same parameters as before, we're able to get to states that are within a few energy gaps of the ground state. And so that is sufficient to reproduce the step scaling function from the previous slide for these lattices. So it appears that sort of experimentally realizable coherence times and control fields in neutral atom systems are good enough for us to begin to reproduce features of the continuum limit of the O3 model, which means we can really not think about this not as just like some simplified toy model, but actually really simulating actual quantum field theory, which for us is very exciting. So future directions, I should mention that all the simulations I showed are just classical simulations assuming unitary time evolutions. So there's no modeling of the effects of decoherence or imperfect control fields and for the neutral stuff, atoms drifting during an experiment. So there's some work for us to do to understand the impact of those errors. And so, like I also mentioned earlier, that we're interested in studying things like scattering between walls, putting excitations on top of the ground state. So we'll need to do a bit more further work to figure out how to do that. There also might be other implementations or applications that this adiabatic spiral technique that might be interesting, since we only really looked at it as a tool for preparing the ground state of the O3 model. But the Heisenberg model also has other interesting properties that you could potentially explore with this. Of course, also, we should also look at running this on hardware at some point. But yeah, so that's all I've got.
Great, thank you very much, Anthony. A round of applause on behalf of all members of the audience, I'm sure. And now I'll open it up for questions if anybody has any questions for Anthony.
I wanted to ask quickly, so there's no problem with the ramp on neutral atoms?
There is not. You're able to ramp off quickly enough that it doesn't create, you don't have the same problem that we saw in the superconducting ones where it stays adiabatic. You're referring to the ramping off, right?
Yes. Thanks.
Sorry, Jack Brennan has a question. Jack, go ahead.
Hi, sorry. I actually missed the first few minutes of your talk, sorry. But I saw your stuff on D-Wave and I work at D-Wave, so I was wondering what your simulations what your simulations indicate as the speed of the ramp required to avoid this returning to the ground state, returning to the prepared state.
I don't recall how fast we would need off the top of my head. Sorry.
I think probably I think like the public rate for the ramp is something like 1 microsecond per unit s,
Mhm.
which is probably the limit you chose. But actually, we can go significantly faster than that. We can also do there might be some possibilities for asynchronous control of the schedules on different qubits and some other things like this that might be exploited. Anyway, maybe I can connect after the talk because I'm quite interested in this preparation.
Yeah, that'd be interesting to explore.
Yeah,
Yeah, we just use the public schedules and parameters for this.
my question is around the same topic, I guess, and maybe Jack is the person to answer this rather than Anthony. I'm not sure, but I'm thinking back to the paper maybe 4 or 5 years ago where D-Wave is doing a reverse anneal on a topologically ordered system, and then you go back to some finite value transverse field, and you quench rapidly and read out, and that seemed to work. And I haven't quite understood why that works, because my instinct would be that even at the non-publicly available quench rates, that there would be significant dynamics during that so-called quench in that paper. So what is it that's different, and what is it that's sort of magic about that that quenching in that particular paper that really doesn't apply in Anthony's presentation here?
Do you want Anthony to answer first and then me, or?
I would also like to know the answer to that question because I'm also confused by that.
Well, my opinion, well, if I recall correctly, what we did there, there's like you have these basically large scale vortices and anti-vortices that are describing the phase at any given time. And when you project out, you have local relaxation of the states, but these macroscopic features are robust to that local relaxation. So then you're able to turn the transverse field back on and reestablish the local quantum phenomena, and you recover the same phase or the same macroscopic. How would I say? You recover the statistics of the macroscopic state you came out of. So there's like in particular that's like a model with continuous symmetry, and I think like the state with the slowest dynamics we found in that model involved like a winding around the boundary, the periodic boundary of this sort of quasi-spin. And so it was very slow for that wound state to unwind into the dominant sort of ground state where all the spins are aligned. So you could quench in and out of that state and sort of somehow it is a bit magical, but yeah, you could recover an interesting time scale for the dynamics of escape from that state.
I guess I can comment.
Yeah, it is a bit. There's a lot of left, especially from a theory perspective. There's a lot left to study in the context of that experiment.
Yeah, I should mention. So for us, because for our system to like not suffer from this going back to your initial state problem, because A and B are on order gigahertz, we probably would require ramp off times that are order nanoseconds. So the time is actually quick relative to the energy gap. I don't know if that is something that's feasible or
yeah, that's possible. There are, I mean, it's are there ways you can lengthen the time scale of your dynamics? Like macroscopic features of this Heisenberg model. Maybe if you choose a larger system, you'll have some slow time scales you can measure. I that won't help you get to the ground state necessarily, but
Yeah, there might be. I haven't thought about this for a while.
Any other questions for Anthony from any member of the audience? Just one quick question. When maybe I missed the explanation of this, but when you first put up the Ising Hamiltonian, there was a Y field. Yeah, here, which clearly is not achievable on a D-Wave device.
Which isn't?
So the
the Y?
The Y term there, that one, yes.
Oh yeah, we just put that there for completeness. We never actually used it.
Not essential. Okay, fine.
Yeah. Yeah,
Okay.
you could use it if like you had access to it, but everything I talked about here, you could do without it.
Okay, fine, cool.
I was wondering whether I could say that we can do some sort of readout at nanoseconds. I think like I think we probably can, not with anything public, but I think there are some engineering features we could explore for that, which is why I'd be interested in connecting after the talk about what your requirements are.
Interesting to talk about.
That is what this network is all about, is introducing to one another so they can collaborate and move the field forward. Very pleased to. But if there are no further questions, let's just thank Anthony once again. Thank you, Anthony. Interesting stuff.
Thank you.
I look forward to seeing everyone at next week's seminar. We'll see you there. Bye-bye.
Yeah, thank you for having me.
Thank you. Have a nice day.